Hi folks, we're going to take a look at an example of an object which is hanging by two strings and is not moving. So we're going to take 2 points along a horizontal line, okay, that are 2 meters apart. Okay, and we're going to have an object that is hanging from 2 strings. Okay, one string is going to be 1.5 meters long and the other string will be 1 meter. Okay, and the object that's hanging is 20 kilograms, so we know that we've got 20 times 9.8 as a force due to gravity. So let's check that out. 20 times 9.8, okay, 196 newtons. Okay, and what we want to do here is we want to find the tension in the 2 strings. So if this is our object, we have the force of gravity acting on it, and then we've got the force coming from the tension in the 2 strings. Okay, so what we want to do is add up all these vectors, these 3 vectors, and because the object is not moving, it means the net force has to be 0. So when we add up these 3 vectors, we should get the 0 vector. In other words, if I add them tip to tail, I should end where I started off. The one thing I'm missing in a problem like this is I don't have any angles to work with. So there's no way for me to draw my vector diagram unless I have a way to determine the directions of these vectors. Okay, and this is when I look at the information that's given to me, and I notice that I have 3 sides of this triangle here, and I can use that to find these interior angles inside the triangle, and those are useful because this angle will be the same as the angle from the horizontal for the first tension, and this angle here will be the same as the angle from the horizontal of this second string. Okay, so I'll call this one theta, I'll call this one phi. Okay, so the first thing I'm going to do is calculate theta. Okay, easy cosine law problem, so I'm going to go straight to writing out my isolated variable. So since 1.5 is the opposite side, we have 1.5 squared minus 2 squared minus 1 squared all over negative 2 times 1. Okay, I do want to show this on the calculator here just to make sure that we're inputting it correctly. Okay, so cos inverse. Okay, now you notice my calculator opens up a bracket for me. If yours doesn't, you should be opening it up yourself. And the other thing I want to be sure of is that I put the numerator all in a bracket and the denominator in a bracket just to be sure that the order of operations is followed. So I'm going to open up my bracket here. So I have 1.5 squared minus 2 squared minus 1 squared. I mean, I really know what 2 squared and 1 squared are, but I just do it so that I keep the habit, divided by. Now I'm going to open up a bracket for my denominator. So negative 2 times 1. Close off the 2 brackets, and I get an angle of 46.57. Okay, so theta is 46.57, which means that this angle here will also be 46.57 degrees. Okay, let me find phi now. Okay, so again, cos inverse. Since I only know one angle in the triangle, you know that I prefer to just keep using cosine until I know at least 2 angles in the triangle if I have a choice. Okay, so here the opposite side to phi is 1, so it's 1 squared minus 2 squared minus 1.5 squared all over negative 2 times 1.5. Okay, and again, let me calculate that here. Okay, we've got cos inverse. Okay, again, open up my bracket for the numerator, 1 squared minus 2 squared minus 1.5 squared. Okay, close bracket, divided by, open up a new bracket for the denominator, negative 2 times 1.5, and close off my 2 brackets, and I get 28.96. Okay. Now that I have directions for these two vectors, I can now draw my vector diagram. Okay, so this is where you have to be careful. You're not going to be calculating anything to do with the sum of the forces on this diagram here, because the forces are all tail to tail. And when we want to add these forces together, we want to add them up tip to tail. So I start with the easiest vector to draw, which would be the force due to gravity. Okay, so I know here that the magnitude of the force due to gravity is equal to 196 newtons. Okay, now because I've written this here, I'll start with my vector going towards the right. So I know here that my angle is 46.57, so I'm going to add my vector here, and I'm going to indicate that my angle is 46.57. Okay, then to that I have to add this other vector, okay, going towards the left, and since the net force is 0, I have to end off where I started, so that my resultant vector is the 0 vector. And here I can add in that my angle is again the same as phi, so 28.96. Okay, so now I can determine my two tensions. So I'm going to start here with, I'll call this T1, and we'll find the magnitude of that, and we'll call this T2. Okay, so let's say we add a little more information in my triangle. So here I see that this is 46.57, so I can determine that angle there. So let's do that here. We have 90 minus 46.57 is equal to 43.43. Okay, by parallel lines, I know if this is 46.57, so will this little angle be 46.57. So I'm going to call that big angle there. I just have to add these two angles. So what do we have? We have 46.57 plus 28.96 equals 75.53. So 75.53 degrees. Okay, now I have this angle and this opposite side, so this is what I'm going to use to determine the other magnitudes. Okay, so I'll start with T2 since I know its opposite angle already. So here I've got the magnitude of T2 over sine of its opposite angle, 43.33. is equal to, and now I'll use the known pair, 196 over sine of 75.53. Okay, so I'm going to calculate all of this at once, and we've got here, okay, so we've got, we'll multiply this out, so 196 times sine of 43.33. Okay, and then I'm going to divide that by sine of 75.53. And we end up with 138.9. So 138.9 newtons. Now, since this was T2, we know the direction. We know that it's, what was it here, 28.96 from the horizontal. Okay, so I can give T2 is equal to 138.9 newtons. Okay, and I'll say it's, again, different ways you can describe this, but it's 28.96 degrees from the left horizontal. How's that? Okay. Okay, oh, there you go. Let's show you what that actually is. Okay, now, if I wanted to refer to this as the negative side, positive side, that would be another way to describe the direction, okay, as long as you're clear as to what you mean. Okay, so now let's find T1, and we'll need this angle here to find T1. So let's calculate that quickly. 180 minus the other two angles, so 43.33, minus this angle here, 75.53, and we've got 61.14. And now I can use sine law again to determine the magnitude of T1. Okay, so let's start with T1 over sine of its opposite angle, which we found was 61.14. And then on the other side, I'm going to use the same known pair. Okay, so we've got 196 over sine of 75.53. And so we calculate the magnitude of T1, and we have here, okay, 196 times sine of 61.14, okay, and we'll divide that by sine of 75.53. Okay, and we get 177.28. 177.28 newtons. So T1 is equal to 177.28 newtons, and let's recall, it is 46.57 degrees. Whoops, let's go there. 46.57 degrees above the right horizontal. Okay, so we can write 46.57 degrees from the right horizontal. Okay, and there you have it. So main thing here is that I use this diagram to set up the situation. I try to indicate all the forces that are acting on my object. Here, though, they're tail to tail. When I want to actually do my sum equaling 0, I actually have to draw a vector diagram, in which case I add up the vectors to 0, so that the resultant is a 0 vector. And in this case here, I noticed that there was information missing in order for me to draw this picture, namely the angles, so I had to do some work first to find the angles. Okay, that's it for now.